have a plate. It's supported by ball and socket joint at point A. Right? Here is the point A, right, where this plate is connected to this, I would say, wall. And then there are two cables, CE and DB. Right? We have to find what we're asked to do is that we are asked to find the tension in each cable. We have two cables. We have to find the tension in these two cables. Now remember that cables are always under tension, right? A cable under compression doesn't make sense. It doesn't exist. If you find out if you end up having a cable under compression, right, it means in that specific configuration, you can remove that cable from the system because it's not really applying any force to your rigid body. All cables and chains and I would say threads should be under tension. Uh, and we're giving the weight of the plate. It's 270 pounds, obviously downward. And as I think I mentioned at the end of the previous class, or maybe I didn't, I'm not sure, that we put the weight exactly in the center of mass, and you don't need to be worried about, but you can see that logically when you have a plate, the center of mass is exactly at the center of the plate, as long as the plate is homogeneous and the mass is distributed evenly, obviously. So pretty much the weight would be somewhere here, and that will be about, this is 8 inches, so that would be, that's very not, that would be 6 feet, so that would be 4 feet, right? 4 feet from this side and 4 feet from that side. All right, let's start with where we always start, right? Free body diagram. Said always start with free body diagram. Draw the free body diagram, look at all the forces, put all the forces on your free body diagram, all the knowns and unknowns, and see and look at this structure or the rigid body, and then take it from there. So let me attempt to draw a free body diagram, at least a plate as close as this one. All right, forces. Now, forces, well, obviously the weight is there, applied to the center of gravity, center of mass, downward. I have two cables, right, BD and CE. And I said they're on tension, so obviously the direction should be in this direction, right? When they are in tension, they're applying a pulling force to a structure. And let's put this one, let's say here. Let me put the names. This is W, so let's call it W. It's 270 pounds. This would be T BD from B to D, and this would be T EC. Let's say from E to C. All right, so far so good. Now, since we're isolating this, right, keep in mind that what we're doing is we're isolating this plate. That's how we draw rigid body, free body diagram. We isolate this. So the only thing left is the connection that this plate had to that wall or support. Now that connection or support is already mentioned in the problem statement. They told us it's a ball and socket joint. Right? So if you go back to the list of different supports or support reactions or different supports that we studied their reactions on the structure, support number 4, which I mentioned that as number 4, that was a ball and socket joint or support. What does that mean? It means if I'm removing that support, I have to replace that support or put forces and moments, if there is any, on the place where that support is, the way that is mentioned here. I have to compensate for that as by putting 3 forces, Fx, Fy, and Fz, or better to say 3 components of 1 force. Technically speaking, it's just 1 force, but it's some random angle in the space. So what we do is that we put its three components in basically in Cartesian coordinates. You can think about this force as just one force that creates angles with different axes. But in this case, it's easier, just that's why you represent things in Cartesian coordinates. So we represent that with x, y, and z components. So keeping that in mind, I'll go back here. I'll try to follow the same way that the book did it. I'll put, this is point A. So I'm getting rid of this support. Now I'm compensating for that support using three components. Right? Let's put this upward. Again, the directions when you are putting the support reactions is not important. Because if the direction is incorrect, at the end, you're going to get a negative value. If the direction is correct, you get a positive value. So if you get a positive value after studying or analyzing the structure, it's a confirmation that the direction you assumed was correct. I'll put this one in this direction. And let's put this in this direction. Yeah, I guess that's how Book did it. So just stick to that. Let's call this A. Oh, these are the coordinates on our system. They're given X, Y, and Z. It's a right-hand rule. Go from X to Y. Should give you Z. So that would be AY. This would be AX. This would be AZ. Just name those. You can use whatever name you want. All right. I can also try to put the axes on this with this danger that things get messy, but let's just try. Let's call this X, this is Y, and this is Z. All right. So I have my free body diagram now. All right. The next step, what we were doing always, right? Once you have your free body diagram, you have to start thinking about writing everything or representing everything. We are in three-dimensional space, so you have to represent everything in Cartesian coordinates. Now, in this case, we have two forces because of the cables. We have a force because of the weight or the loading because of the weight, and we have the components of the force at point A. So I'm going to write it. Let me write it like this. So F A, called FA at point A. So I'll call it AX in I direction plus AY in J direction plus AZ in K direction. I don't know these components are unknowns. Now I want to write the components of the force for TEC. How do I do that? What is the step that I have to take before trying to write TEC in Cartesian coordinates?
Do you find like a point that represents E and C first?
Exactly. And let's just write all the points, because later on I want to represent TBD, so I need to know the coordinates of B and D. Right? For TEC, I need to know the coordinates of E and C. Remember, we need to know the coordinates of 2 points, and then use those two coordinates to find the unit vector and represent this force in Cartesian coordinates. So I'll write the coordinates of all the points. You tell me what is the coordinate of A? Well, A is the origin, so 0, 0, 0, right? Coordinates of B, what is that? B here, right? It's on x-axis, so pretty much just 8, exactly. Thank you, Elizabeth. 8, 0, 0. Then point C, I don't know, maybe I shouldn't put these commas here, so I should be more confused. Point C, which is right there. Well, X is 0 for that point. Y is 3, go up 3 units, 3 feet. And Z is 2. Let's also do that for point D, E, and any other point. Let's just do it for D and E. Point D, X is 0, 4, 8, yes. 0, 4, well, minus 8, exactly. Since point D is indeed the negative side of the z-axis. Point E will give us, it only has X component, right? So 6 units in X direction, 6 feet, 0 and 0. I don't know if I need the, let's just write that too. I'll call that point F. We're going to need this later, where the center of gravity is, or where the loading is applied. You'll see later on why do we need that. So what is the coordinate of this point? This is also halfway through. I'm making it very messy here, but this is also halfway through this. So this is 2.5 feet. So what would be the coordinate for point F? 4 minus, exactly. Thank you, Richard. 4 minus 2.5 and 0. So now we have the coordinate for point F. All right. Let's keep these here. I'm going to keep going back to these points. So I'm just going to identify or separate them from the rest of the story. So I wrote F in Cartesian. Now I want to write TEC in Cartesian coordinates. TEC would be the magnitude of TEC times, right, let's write the unit vector. EC, so I'll find the difference between each component for these 2 points. So 0 minus 6 will give me minus 6i. 3 minus 0 will be 3j. And 2 minus 0 will be 3k. The magnitude of this, well, I'm finding the unit vector, right? So I'm dividing, we talked about this. We have to actually get rid of the dimension, because if you do not divide it by the magnitude, you are going to have a vector that has unit, in this case, feet. But we don't want a vector with a unit, so we divide that by its magnitude. So whatever is the unit of the vector, which is feet, divided by feet, you're going to have a unit vector without a dimension, which is what you want, because you want the TEC to be in this case, pounds. TEC, the magnitude is in pounds. It's multiplied by some dimensionless number, so it's still in pounds. So minus 6 squared plus 3 squared. If you did not exactly follow what I just said, don't be too worried about that. It was just the logic of why we use the unit vector. All right, so this gives TEC as a vector as the magnitude of TEC, which we don't know and we want to find, multiplied by the unit vector that comes out of this fraction. That will be minus 0.857i plus 0.428j plus 0.286k. It's the first, oh, this is the second. So I represented F in Cartesian coordinates. I represented EC in Cartesian coordinates. I'll continue doing that. I'll go for TBD. Let's represent TBD also in Cartesian coordinates. So that would be TBD, the magnitude multiplied by whatever is this vector. Now BD means components of D minus components of, right, BD, components of B. So minus 8, 4, minus 8. So that would be minus 8I plus 4J minus 8K. And divide that with the magnitude of this vector. So we get the unit vector. 4 squared plus minus 8 squared. Now if you do this math, you will get the magnitude, which we don't know, multiplied by, I have the unit vector somewhere there. I did, okay, minus 0.667I plus 0.333J, and same thing, minus 0.67K. Also, this is TBD now in Cartesian coordinates. Other force we have, the only thing left is the weight, right? And it's downward. So it's W is, we're given the value 270 pounds, would be minus 270 pounds J. W, the weight would be minus 270 pound J. I have to be more diligent and put the units for these. All of these are in pounds. Don't take me as a good reference for putting units. You always put the units. They should always be there. Numbers with no units, they don't make sense. All right, so let's use the first set of equations we have, right? If we go back to when we were talking about all the way at the beginning, right? We said we have the summation of forces equal to 0 and summation of moments about a specific point is equal to 0. Let's form the summation of forces equal to 0. Right? So now we can write summation of forces is equal to 0 since it's in equilibrium. Right? Newton's first law. If we do that, let's sum up the x components for all of them. We have AX from FA, and we have minus 0.857 from TEC. We have minus 0.667 from TBD. So I'm just going to put them all together. It's AX minus, I think I said 857 TEC. I'll check it. Minus from here 0.667 TBD. Right? This is I. Other way would be the way I usually write it, just separate them in X, Y, Z components and make them equal to 0. I'm just writing it this way first and then do that part. The second part would be AY. FA has AY in Y direction. TEC has 0.428 in Y direction. And TBD has 0.333 TBD in J direction. So that will be AY. Let me double check. I forgot the number. 4.28. Yes, 4.28. I meant 428 TEC and plus 0.333 T. I'm trying hard to put it here. TBD. Let me not squeeze this there. Plus 0.333 TBD. That would be all the J components or components in J direction. That is true, and also weight. Thank you. You should not forget the weight. W also is here, right? I should have underlined this. There we go. So that would be minus 270, and in J direction. And finally, all the components in z direction. Well, we have az from the first one, which we don't know what the value is. The second one for TEC, you have 0.286. So that would be plus 0.286 TEC. And the last one from the vector of TBD would be minus 667 TBD. This is in K direction. Hopefully I did not miss anything. Now, putting them separately in equations, obviously we're going to get three equations. Like the first one comes from the first part, 857 TEC minus 0.667 TBD is equal to 0. Right? If this vector is equal to 0, all the components should be equal to 0. AY plus 0.428 TEC plus 0.333 TBD. I can move 270 to the other side. And then the last one would be AZ plus 0.286 TEC minus 0.667 TBD is equal to 0. All right, looking at this, right, I'm giving you all the details at least for this example, because this is the first example we're solving. We're going through. So this is, we have three equations, but we have 5 unknowns. It's a set of equations. Mathematically speaking, we cannot solve this, right? We don't know the magnitude of TEC or TBD. We also don't know the values for AX, AY, and AZ. So, right, let's keep this here, equation star. This means we need more equations. Right? We only have 3 equations, but we have 5 unknowns. So we have to generate or produce more equations to have enough equations for the number of unknowns we have. How do we do that? Well, it's a rigid body in 3-dimensional space. So as I said, right, the second set of equations right there, right, now we have to find a moment about a given point. So go back. Which point I have to choose to find the moment about? Looking at the free body diagram. Point A. Yes, Richard, right? A, exactly. Why? Because we have the most number of unknowns. And remember, when we are finding a moment about a given point, if a force is, or the line of action of that force is passing through that point, the moment about that point is 0 for that force. So if I find the moment about point A, pretty much AX, AY, and AZ are going to be out of the picture. Right? They're not going to create any moments. So let's do that. But keep in mind, if I want to do it, what do I need to know now that I do not have it? I need to know, right, I'm finding the moment. Right? Let me just write it first, and then I'll, so let's find summation of moments about point A, which is equal to 0. Well, in this case, we're in 3 dimensions, so no specific, just take it as vector. All right, so this one, if I want to find the moment about point A, the vector, well, I have to find R E cross TEC, right? And RE being the vector or position vector from any point on the line of action of TEC to point A. Now I'll choose the easy point. I'll choose it here. I'll call this RE. Position vector for TEC. Because I need the R, the distance that force or any point on the line of action of that force has from the point I'm finding the moment about. Right? Remember when we were talking about moments in 3-dimensional space. So RE, Well, again, remember, RE could be from point A to any point on this line of action. I just chose this because that's the point, that's easiest point, and I know the coordinates for that. And the same logic, I'll take this as RB. And finally, I need R. Let's call this RF, I guess. Since like, I call this point F, yeah. Oh, maybe that was not a good name because then you're using F for the force. All right, let's call this RF, given that this is point F. So I know these forces, they are represented in Cartesian coordinates. I have to find these position vectors in Cartesian coordinates. Right? Let me finish the equation for a moment. So this would be RE cross TEC plus RB cross TBD plus RF cross W. And this should be equal to 0. These are all the forces that create moment. If you look at this free body diagram, we have TEC, TBD, and W. A components of A are obviously passing through point A, so it doesn't really matter. All right, so I already know TEC, TBD, and W, or I already have the representations in Cartesian coordinates. I have to find the representation, or I have to write RE, RB, and RF in Cartesian coordinates. Right? That's what I need. So RE, RB, and RF. These are what I want. Now, looking at this free body diagram and the coordinate system, you tell me, what is RE? It's a vector from A to point E exactly on x-axis. And it's a position vector, exactly, 6i. Right? Thank you, Elizabeth. So this is 6i. What is RB? RB, well, going from point A to point B, again, on x-axis, 8i, exactly. Thank you, Richard. That would be 8i. Now, how about F, RF? RF actually is in XY plane. It has components, both, it has a component in X direction, it has a component in Y direction. It has no component in Z direction. And it starts from the origin. So how do I represent RF in Cartesian coordinates? 4i minus 2.5j, exactly. Thank you, guys. 4i minus 2.5j. Make sure that everybody saw that. Right? So we have in this direction, let me use something that's less. Okay, so it has two components, right? In X and Y. In X direction, well, that would be, let me just do it here so it's less crowded here. Is RF in X direction. This is RF in Y direction. RF in X direction is 4. RF in Y direction is minus 2.5, since it's in Y direction in negative side. Or along Y-axis in negative direction. So that'll give me 4i minus 2.5j. All right. So now we can find these. Let's go one by one. Call this 1, 2, and this is 3. From 1, right? Very nice color code following. All right, so orange 1 would be RE cross TEC. How do we do this cross product? Well, the first row would be IJK. RE has only 6, a component in I direction, so these two are 0. And TEC, if we go back to TEC we had from before, right? TEC there, like IJK components, just plug in there. First one, I think minus 0.8. Let me check what I have. 5.7. I could do a better job. Let me just expand this a little bit. So when you look at this later on, it's not confusing. Let's do it this way. IJK, right? And then we have component 6, 0, 0. And for TEC components, we have it from before is minus 0.857. Point TEC. It seems like I still have to write it in more expanded way. 428 TEC. I'm sorry for the bad representation of the vector here. TEC. So if you do this math, if you find it determinant, right, for this one, you're going to get, let me see if I have it somewhere here. Yes, so you're going to get minus 6 times 0.286 TECI plus 6.428 TEC. Okay, given that I didn't make any mistake. Same story for the second one, right? We'll get RB cross TBD. This time I learn my lesson. Let's make it bigger. IJK. RB is 8. So let me just put 8, 0, 0. And the components of TBD, we have those components from before, right? We found them here. So just plug them there. That will be minus 0.667 TBD. For one, isn't the I unit supposed to be J? Huh. Yes, it should be J. Since I got rid of that, thank you. Exactly, it should be J. This is J. And that's how, my friend, you lose point on the exam, right? 0.333, thank you, Bobby. 3 TBD, and then minus 0.667 TBD. If you do this, get rid of this one, this should give us minus 8 minus 0.667 TBD J plus 8 0.333 TBD K. All right. Last one, almost there. You do R, F, cross W. So let's do this one. Let me see if I can expand this a little bit. Maybe I can't. Okay, I'll just write it. I, J, K. Right. RF is 4I minus 2.5J and 0. And then the components for W is basically just 0 minus 270 and 0. Right. And this just pretty much gives you 4 times minus 270. Okay. All right. So we calculated all the components for the moment about point A. All we need to do is just put them together. Right? There is no I component, so just sum up the J components and sum of all the k components. So if I want to write it again here, summation of all moments about point A should be 0. This means that I actually did the math there. So minus 1.716 TEC plus 5.336 TBD would be the J component, plus 2.568 TEC plus 2.664 TBD minus 1080 would be your K component, equal to 0. So from there, or since this is equal to 0, all the components should be equal to 0. You could just write this directly without writing them in the vector form and just put every set of equations equal to 0. This will give you, well, let's go with 5.336 TBD. I'll move that to the other side, 1.716. Oh, let's write these two equations to unknown. It's easier to actually, if you're using a calculator, it's easier to 6T EC is equal to 0. For the K side, 2.664 TBD plus 2.568 TEC is equal to 1080. Now this is two equation to unknowns, right? This is two, let me write it here. Equations and two unknowns. So from there, you can actually find, mathematically speaking, once you have two equations and two unknowns, you can actually find the values. You do the math, I'll give you the final answer. TBD and TEC becomes, well, you know, we can also check the textbook, obviously. 101.41 pounds, and TEC, remember, these are the magnitudes, 315.354 pounds. Right, so we found TBD and we found TEC. Now, if you look at the problem statement, right, that's we were asked to find the tension in each cable, which we did, and now we have to find the reaction at A. Now, reactions at A, we go back to this set of equation. We had 3 equations to 5 unknowns. We now have TEC and TBD, so knowing those, we can just plug them in here, and from the first equation, we'll get AX, from the second one, we'll get AY, and from the third one, we'll get AZ. Well, as easy as that. Because then that set becomes 3 equations and 3 unknowns. So from star AX, AY, and AZ, I found them as let me just give the final number, 333.9 pounds. AY would be 101.228 pounds. AZ would be minus 22.58 pounds. From there, you can actually represent FA if you want to make it more like a vector. Obviously, 33.9 I plus 101.228 J minus 22.58 K. And that would be the reaction at A. This is also pounds.